Greeting to Dr. Novaya. Today me and my group member going to present about FSK and QPSK modulation and demodulation. And this is my group member Rubaraj, Kidiga, Pravinraj, Tioli, and me Ravinesh. Okay, now I'm going to talk about the FSK introduction. The frequency of a frequency shift key transmitter is shifted by the message. As the name implies, frequency shift key FSK is a discrete signal transmission method for a digital signal. In a binary frequency shift key mechanism, the two binary state logic 0 low and 1 is high, both represented by the analog waveform, which means FSK is a transmission method for a digital signal. As we know, digital signal always 0 or 1. So in a binary FSK, the logic 0 is low and logic 1 is high, both represent as an analog waveform. So a wave with a given frequency represents logic 0, while a wave with different frequency represents logic 1. The deviation or shift point is a distance between logic 1 and logic 0. A modem translates binary data from a computer to a frequency shift key FSK for a transmission through telephone line, cable, optical fiber, or wireless media. As you can see from the picture below, the first one is the information signal, the second one is the carrier frequency 1 and second, and the last one is the modulated wave for carrier frequency 1 and 2. It means a combination. So as you can see here, this is our block diagram. First one with AWGN and without AWGN. So Bernoulli binary generator function. The Bernoulli binary generator block generates random binary numbers using a Bernoulli distribution. This block can generate random data bit to simulate data communication system, which is mean that the Bernoulli binary generator function creates a information signal. That means it's a information signal. So the next one is the charge pump PLL. The charge pump PLL phase lock loop block automatically adjusts the phase of a locally generated signal to match the phase of an input signal. It is suitable for use with digital signal. Okay, this is our FSK simulation output with AWGN and without AWGN. So what can we observe from this is output whenever our input binary is 0, the modulated waveform will be low frequency, while input binary 1 modulate waveform will be high frequency. So with AWGN, when we doing FSK with AWGN, we observe that they are not much different than without AWGN output waveform. But when we are using MATLAB coding, we able to observe the noise in FSK with AWGN.
Okay, next I will show the step to do the FSK modulation and demodulation in MATLAB. Firstly, we clear all the command window and close all the figures, and then we will set the binary information sequence and set the bit periods. So now this is the step to convert the binary information into digital signal, and then this step is to plot the digital signal graph. So next we will do the binary FSK modulation. So firstly, we set the amplitude of carrier is 5 watt, and then we set the bit rate, and we set two frequency, which is the first frequency for bit 1 and the second frequency is for bit 0. And then this is the step we plot the binary information. We plot the waveform for binary FSK modulation. So next we will plot the another FSK with noise. So next we will do the FSK demodulation. So this is the step to do the demodulation, and then we will get a binary information at a receiver. Next we will convert the binary information into a digital signal. at this step. And then lastly, we will convert the digital signal. We will plot the digital signal at this step. So that's all. Okay, next I will show the step to do the FSK modulation and demodulation in MATLAB. So firstly, we'll clear all the comments and close all the figures. Next, we will set the binary information sequence and set the bit period. Next, the step is to convert the binary information into digital signal. And then next we will plot the graph of the digital signal. Okay, first after that we will do the FSK modulation. Firstly, we set the amplitude of carrier signal is 5 volt, and then we set the bit rate and set the two frequency. The first frequency F1 is the frequency for information as bit 1, and then the second frequency, which is F2, is carrier frequency for information as bit 0. So next we will plot the waveform for FSK modulation, and we plot another FSK modulation with noise, which is represented by this step. Next, we will do the binary FSK demodulation. So all of this step is the demodulation, and we will demodulate the modulated signal, and then we will get a binary information at receiver. Next, we will convert the binary information into a digital signal. And lastly, we plot the demodulated digital signal graph. So now I will run to show the waveform. Okay, so the bit sequence that we set just now is 0001 and 0111. So this is the binary information. This is the binary signal. Next, this is modulated signal, and this is modulated signal with noise. And lastly, it is a demodulated signal, digital signal. Okay, that's all.
Hi, I'm Kirtika. Okay, next let me explain about quadratic phase shift keying. QPSK is a modulation technique where two bits are encoded simultaneously by selecting one of four carrier phase shifts: 0, 90 degrees, 180 degrees, or 270 degrees. This allows QPSK to transmit double the information compared to standard phase shift keying, that is PSK, within the same bandwidth. Employed in applications such as satellite transmission, cable modems, video conferencing, and cellular networks. QPSK efficiently utilizes RF carriers, making it integral for various digital communication forms, particularly in scenarios demanding high data throughput over limited bandwidth.
Hello, good evening. Today I'm going to talk about the QPSK modulation and demodulation. So I'm going to show step by step before I run the simulation. So as the input, we are using the random integers. So the random integers is we are set the set size to 4 and others all as default values. So the random integers is to give some random input binary numbers, and then we are using QPSK modulator baseband. And the settings are, we just change the phase offset to the pi over 4, and others are default setting. And we are using also AWGN channel to generate the noise. These are also the default setting for this block diagram, and also QPSK demodulator baseband. So we change the phase offset same as the modulator baseband, which is pi over 4. And we are having two scopes, scope 1 which will shows modulated output, and scope 2 will shows demodulated output. and this constellation diagram is to show the noise that will came out from the AWGN channel. And we are, for the modulated output, we're using two sine wave. For the one is sine wave, another one is cosine wave, and these both will be combined and will times, which is will be product and will be plus together, and then only it will form the modulated waveform output. So now we are going to see the output when we run. Okay, so this is the constellation diagram, and these four red dots are the actual place where the signals are going, and these yellow dots are the noise that is generated by the AWGN channel. And then we're going to the scope for the modulated output waveform. So we can see here, this is the input signal, and this is the QPSK modulated wave. So we know that QPSK it will modulate two bits binary at once, and it also has four possible carrier phase shift, which is 0, 90 degrees, 180 degrees, and also 270 degrees. And so now we can see at here the first place, the first part of the QPSK modulated waveform, we can see that it shows 0 degree because there is no change, and the second one also it shows a 0 degree with no changes. And then the next one, we can see this is 180 degrees, and this one also normal, which is 0 degrees, and this one shows 90 degrees because it's come from here, and another, we are having another 180 degrees at here. And then here the straight line, this one is for 270 degrees, and same, yeah, this one also 90 degrees. So this one is the QPSK modulated wave. Now we are going to see for the QPSK demodulated wave. So what we are gained from this is the input wave is similar to the demodulated wave, so we are getting the same, exact same as the input wave for the demodulated wave also. So that's all for this QPSK simulation. Thank you, and I'll pass to my next team members. Thank you.
Okay, now I'm going to explain about QPSK coding. First, we start with our first line, which is clear command. We use this clear command just because we have two progress in this coding, which is modulation and demodulation. So now we start our simulation for modulation. So the modulation will run, then once complete, the modulation process will stop and the demodulation will start automatically. If we not use the clear command, once complete the modulation, the modulator process still will run while the demodulation process running. Okay, then in line 5 we can see an array data is created to represent binary information, and then in line 6 to 10 this will create a plot to visualize the binary input data. Okay, then line 11 to 12 it converts the binary data to non-return to 0, which is NRZ format, and then it will reshapes it for quadrature phase shift in QPSK modulation. Okay, in line 14 to 29 the QPSK modulation will start. Okay, in line 14 to 29 this line section will perform QPSK modulation, creating by in-phase and quadrature components and combining them. In continuously, the line 31 to 33, it adds AWGN to the modulated signal to simulate real-world conditions. And then the line number 32, the variable SNR dB represent the signal to noise ratio in decibel. SNR is a measure of the quality of communication channel, indicating how much signal power is present compared to the noise power. In this case, an SNR of 10 dB is specified. Okay, in line number 33, the function AWGN adds additive while Gaussian noise to the input, and then the modulated signal before to the addition of SNR dB, the signal to noise ratio in decibels. So the result TX SIG is the transmitted signal after the addition of AWGN. Okay, in continuously, we take a look for line 32 until line number 53. Okay, this plots the in-phase quadrature and modulated signal, which is AWGN, to visualize the modulation process. Okay, the line number 35, this is a line generates a time vector for plotting. It is created from t over 99 to t times length over 2 with the step size of t over 99, and this time vector is used to plotting the waveform. Now line number 37 to 41. Okay, this block creates a subplot in the position 1 out of 3 and plots the in-phase component Y-in of the QPSK modulation against the time. Okay, it sets the title and labels for the interpretation. Okay, now line number 49 to 53. In the last subplot 3 out of 3, it plots the QPSK modulated signal with the added AWG and TXSIG. Okay, this visualizes how the signal appears after modulation and how noise affects it. And lastly, we can see that the QPSK demodulation process starts in line number 56 to until line number 69. Okay, this section performs QPSK demodulation by integrating the received signal for in-phase and quadrature components. Okay, this line number 56 to 57 initializes an empty vector of Rx data to store demodulated data, and RxSIG is assigned the received QPSK signal for demodulation. And line number 58 initiates a loop that processes the received signal in chunks corresponding to the original date. And then the line number 65 and line number 66 is similar to the in-phase component, calculates the quadrature coherent vector and Z at and it its integrated value z and okay. Lastly, the line number 72 until line number 76 plots the demodulated data in the second subplot. The title and axis limits are set for the better visualization. Okay, now we can see the output from this coding that we have simulate from here. Okay, once we click the simulate button, okay, the output will be appear now. Okay, that's all from me. Thank you.
Next, let me see what are the difference between FSK and QPSK. As you guys can see here, this is the FSK block diagram and QPSK block diagram, and that is our output waveform for FSK and QPSK. Okay, next let me explain in detail what are the difference between FSK and QPSK. According to signal constellation, FSK exhibits larger signal constellations compared to QPSK. QPSK has more compact constellation indicating higher spectral efficiency. Next, according to spectral efficiency, QPSK's compact constellation result in more efficient use of bandwidth. QPSK is favorable in scenarios where spectrum utilization is critical. Thirdly, according to noise sensitivity, QPSK may offer better noise resilience due to its compact constellations, and QPSK has potential advantages over FSK in noisy communication channels. Lastly, according to complexity, implementation complexity in terms of hardware and computational load varies between FSK and QPSK. And then choice depends on the application's demands, balancing complexity against performance requirements. Okay, lastly, in conclusion, modulation techniques known as frequency shift keying (FSK) and quadrature phase shift keying (QPSK) are essential to digital communication system. Secondly, QPSK is distinguished by its effectiveness in transmitting information and is characterized by using phase shifts to encrypt data. Higher data speeds within a given bandwidth are possible because each symbol is represented by 2 bits and contains 4 distinct phase shifts. Thirdly, FSK uses multiple frequencies for binary representations and frequency fluctuation to indicate different digital states. Precise frequency and phase alignment are guaranteed by the constant application of a pi/4 radian phase offset in the QPSK modulator and demodulator, which makes accurate demodulation possible. Fifthly, to make the simulation more realistic, with Gaussian noise introduced using the AWGN channel, simulating actual noise effects in communication channel. Lastly, the switch block is an essential component in both FSK modulation and demodulation because it controls signals flow by deciding whether to employ carrier signals with higher or lower frequencies in response to control the input. Okay, that's all from us. Thank you.